Welcome to this expert technical training module. Today, we are exploring the fascinating mechanics behind artificial intelligence by identifying AI model components and describing exactly how generative AI models work. Welcome everyone to this expert-level technical training module. Today, we are undertaking a deep dive into the core components and configurations that make artificial intelligence function, specifically focusing our attention on describing exactly how generative artificial intelligence models work. Generative AI is a revolutionary branch of artificial intelligence that empowers software applications to generate entirely new, original content from scratch. While we often associate this exclusively with natural language dialogues and text generation, the underlying technology is fully capable of synthesizing images, video sequences, computer code, and other complex data formats. At the very heart of these astonishing capabilities are what we call language models. These models are highly sophisticated mathematical engines that have been trained on staggeringly massive volumes of text data, typically sourced from the public internet and other comprehensive document repositories. But how do these systems actually generate a response that makes logical and grammatical sense? The secret is that generative AI models work by deeply encapsulating the semantic relationships between thousands of language elements. In technical terms, the model mathematically maps how specific words and phrases relate to one another within varying contexts. When you interact with a generative AI model through a natural language prompt, the model leverages those learned mathematical relationships to initiate the generation of a meaningful, highly relevant response. It functions much like an incredibly advanced, immensely scaled-up version of the predictive text feature on a smartphone, analyzing the sequence of text you provided and calculating the absolute most probable continuation. In this session, we will look under the hood to understand the specific architectural components that make this possible. To understand generative AI programmatically, you do not necessarily need to write the complex deep learning algorithms from scratch. Instead, as enterprise developers, we typically utilize cloud-based APIs to pass raw string data to these pre-trained model endpoints. Within your application code, you are actively configuring specific hyperparameters, such as the temperature setting, to strictly control the deterministic or creative nature of the generated output sequences. This flowchart visualizes the high-level operational flow of a generative AI model. To truly comprehend how a generative AI model works, we must first examine exactly how it ingests and prepares raw data. Computers do not inherently understand raw text strings, linguistic syntax, or English grammar. At their core, they are only capable of processing numbers. Therefore, the absolute first step in preparing training data, or processing a prompt for a language model, is a foundational procedure known as tokenization. Tokenization involves taking a massive corpus of training text and systematically breaking it down into distinct, highly manageable units called tokens. While it is conceptually easy to think of a token as representing a single word, in mathematical reality, tokenization is much more granular. Tokens can represent whole words, but they also frequently represent subwords. For example, isolating the prefix "un" in unbelievable, as well as individual characters, numbers, and common punctuation marks. Once the text is successfully broken down, each distinct token is assigned a unique integer identifier. For example, the word "I" might be assigned the identifier 1, heard might be mapped to 2. The latest generation of large language models boasts vast vocabularies consisting of hundreds of thousands of these distinct tokens. When you submit a prompt, the system instantly tokenizes your input string, converting human language into an array of integer identifiers that the mathematical model can actually process. This foundational component acts as the critical bridge between abstract human communication and rigid machine computation. It ensures the model can handle a wide variety of inputs. If you implement tokenization in your codebase, you utilize a dedicated tokenizer library matching your specific model. Your Python script passes a raw text string directly to the tokenizer's encode function. The executed code then returns a structured list of integers, which serves as the actual tensor input payload fed into the machine learning model's first neural network layer. Observe this diagram illustrating the tokenization pipeline. Raw unstructured text is passed into the tokenizer engine. The engine actively splits the text into words and subwords, proceeding to assign unique integer IDs to each element. This process successfully creates an array of numerical tokens, which serves as the direct machine learning model input. Once our text is tokenized into integer identifiers, the generative AI model must determine exactly how these isolated numerical tokens relate to one another in a linguistically meaningful way. It achieves this profound understanding by assigning each unique token to a vector. In data science, a vector is simply a structured array of multiple numeric values that represent precise coordinates within a highly complex multidimensional mathematical space. Each element, or specific dimension within this vector, acts to encode specific linguistic and semantic attributes of that token. In modern large language models, these vectors do not just possess 3 or 4 dimensions. They are incredibly dense arrays, often featuring thousands of distinct dimensions. During the model's exhaustive training phase, the values within these vector dimensions are continuously adjusted based on exactly how the tokens are utilized within the massive training text. When tokens are frequently used in highly similar contexts, their vector values naturally align, pointing in mathematically similar directions within that multidimensional space. For instance, the encoded vectors for dog and puppy will ultimately end up mathematically much closer to each other than they will to the vector for an unrelated word like skateboard. When these vectors are fully contextualized based on their surrounding tokens, we refer to them officially as embeddings. Embeddings are the absolute secret sauce of semantic understanding in artificial intelligence. They effectively transform discrete, mathematically unrelated integer IDs into a deeply mapped representation of human language. While application developers rarely calculate raw embedding vectors manually, you will frequently interact with them by using specialized embedding models via an API integration. In Python, you can send a raw text string to a dedicated embedding endpoint, and the JSON response payload will contain a large array of floating point numbers. This massive array is the embedding vector, which you can securely store in a vector database to execute advanced tasks like semantic search or data clustering. Here we see the transformation of tokens into embeddings. The integer token IDs enter the embedding layer, where they map to multidimensional vectors. The complex embedding vectors we just discussed are primarily processed by a specific, highly advanced type of neural network architecture called a transformer. Transformers completely revolutionized natural language processing and serve as the foundational engine behind virtually all modern generative AI models. However, before the transformer model can accurately process the embedding vectors, we must programmatically solve a critical linguistic problem: word order. In human language, the sequential order of words completely dictates grammatical meaning. The sentence, "the dog chased the cat," implies something entirely different than "the cat chased the dog," even though both phrases utilize the exact same tokens. Because transformer networks are designed to process tokens in parallel rather than sequentially, they inherently lose track of the order of the words during computation. To rectify this, generative AI models utilize a crucial mathematical component called positional encoding. Before the token vectors are ever fed into the transformer's core processing blocks, a precise positional encoding value is mathematically added to each token's embedding vector. This supplementary piece of dimensional data explicitly indicates to the network exactly where that specific token appears within the input sequence. For example, it tells the model mathematically that the token for I is located at position 1, and heard is at position 2. By injecting this sequence data directly into the mathematical representation of the token, the transformer network can seamlessly process massive amounts of data in parallel, while perfectly maintaining the strict grammatical context of your prompt. Within a deep learning framework such as PyTorch or TensorFlow, positional encoding is typically implemented as a dedicated matrix addition function, placed immediately after the initial embedding layer. The backend code dynamically generates a vast matrix of alternating sine and cosine mathematical functions, based on the maximum sequence length. This matrix is then added element-wise to the tensor containing the word embeddings, before routing the data forward. This flowchart highlights the critical positional encoding step. The semantic embeddings flow into the positional encoding function, which generates mathematical sine and cosine matrices. With our language tokens successfully converted into dense vectors and positionally encoded to preserve grammar, they finally enter the core processing blocks of the transformer model. A primary, defining component of this neural architecture is the sophisticated attention mechanism, which is utilized extensively within the encoder block of the network. The attention layer's primary computational job is to consider each input token individually, while simultaneously examining all the other tokens surrounding it in the sequence. It rapidly calculates a mathematical weight for the surrounding tokens to accurately reflect exactly how much influence they should have on the current token's semantic meaning. For example, if the input sequence is, "I heard a dog bark," when the model evaluates the specific word bark, the attention mechanism will assign a significantly higher mathematical weight to the related words heard and dog than it will to the words I or a, because those verbs and nouns provide the critical linguistic context required for understanding. To make this unbelievably complex calculation highly efficient and scalable, modern models use a technique called multi-head attention. This means the model evaluates multiple different contextual relationships completely in parallel across several independent attention heads. The diverse results from this layered attention process are then seamlessly fed into a fully connected feed-forward neural network to calculate the final, deeply contextually enriched embedding vector for every single token in the vocabulary. Architecturally speaking, implementing self-attention in your code involves explicitly calculating three distinct mathematical matrices for each individual token: query, key, and value matrices. The deep learning code computes the dot product of the query and key matrices to accurately determine the final attention scores, or mathematical weights. These precise scores are then multiplied by the value matrix to output the newly focused vector representation. Review this diagram detailing the encoder block's functionality. Sequenced vectors enter the transformer encoder block and hit the multi-head attention mechanism. The system calculates query, key, and value matrices to determine contextual token weights. These weighted values pass through a feed-forward neural network, resulting in the final enriched embeddings. Once the transformer model has fully processed and encoded the deep semantic context of your input prompt, it must actively generate a coherent response. This critical generative phase is exclusively handled by the decoder block of the transformer architecture. The decoder's singular computational purpose is to iteratively predict the absolute best next word in a sequence, relying heavily on the contextual foundation established by the starting prompt. It achieves this by mathematically evaluating the probability of every single token contained within its massive vocabulary, and then selecting the one token that is statistically most likely to logically follow. To successfully train this decoder block, machine learning engineers utilize an advanced training technique known as masked attention. During the training phase, the model is fed a known sequence of text, but the tokens that logically appear after the current token are computationally hidden or masked from the model's view. The model then attempts to predict the next token. Because the training system already knows the actual next word, it can accurately calculate its own error rate and meticulously adjust its internal mathematical weights to improve future predictions. In a live production environment, this predictive process happens iteratively and rapidly. The model takes your user prompt, predicts the single most probable next token, appends that new token to the running sequence, and then feeds the entire sequence back through the decoder to predict the subsequent token. When enterprise developers consume a generative AI model via a cloud SDK, this highly iterative internal decoding process is completely abstracted away. However, you can interact directly with the token stream by using specific streaming API flags. By setting the stream parameter to Boolean true in your Python request code, the server will return each predicted token individually, allowing your front-end UI code to render the response text sequentially in real time. This workflow illustrates the iterative generation phase within the decoder block. The enriched embeddings are processed via masked attention. The system then evaluates vocabulary probabilities and selects the highest probability token. This token is actively appended to the output sequence, and the entire process iterates until a predefined stopping point is successfully reached. Understanding the complex internal mathematical mechanics of a generative AI model powerfully highlights just how utterly critical your specific inputs are. The model's final probabilistic predictions are entirely driven by the context it receives from the user. This essential context is securely established through the use of precise prompts. System prompts define the model's overarching behavior, professional tone, and operational constraints, acting as its foundational system instructions. User prompts, conversely, are the specific functional questions or commands you submit for execution. Because the model strictly predicts the next token based on the entire preceding sequence, AI applications must actively maintain a robust conversation history, consistently passing previous questions and generated answers back into the model to maintain an ongoing contextual state. To make these probabilistic models highly accurate and relevant to private enterprise data, architects deploy a pattern called retrieval augmented generation, commonly known as RAG. RAG applications query a secure database, retrieve verified factual documents, and inject that strict data directly into the prompt before the model decodes its response. Ultimately, these generative AI models serve as the cognitive brain for advanced AI agents, software applications that can reason over natural language and orchestrate complex tasks. Thank you for joining this deep dive. Please like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, ebooks, audiobooks, advanced training, and interview guides. In a robust Python application utilizing the RAG architectural pattern, your application code first intercepts the user's raw prompt and executes a rapid vector search against an Azure AI search index. The code securely retrieves the top matching document chunks and dynamically formats a new request string, concatenating a strict system prompt, the retrieved knowledge chunks, and the user's original question into one massive payload sent directly to the inference endpoint. Our final diagram maps the retrieval augmented generation architectural pattern. The user prompt simultaneously triggers a knowledge-based search and combines with the overarching system prompt. The system retrieves contextual documents to construct an augmented payload. This highly detailed payload drives the generative AI model inference, producing an accurate grounded response.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by Quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now, the third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology-wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepared for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechit.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.